Hello everyone, we're the UCI Modular CubeSat team. My name is Arlene Erickson, I'm the project lead.
I'm Elena, I'm team manager.
I'm TQ, I'm part of systems engineering.
Eduardo, part of the solar team. My name is Benjamin, I'm the thermal lead.
My name is Baldwin, I'm part of communications.
Okay, so a little bit of background about CubeSats. CubeSat is a nanosatellite with a standardized size of 10 by 10 by 10 centimeters, which makes up one cube. Our CubeSat is a 2-unit, and it also has standardized requirements outlined by NASA. CubeSats are low cost and perfect for small experimental payloads just like ours. This right here is a 1.5 CubeSat. Our mission statement is to design and build a nanosatellite that will be launched into low Earth orbit and perform a 6-month mission. And we aim to build a framework for future missions and payloads for students and professors. So some of our project objectives are to build a functioning transceiver and ground station, build custom solar panels, integrate the payload into the CubeSat design, maintain temperature control of critical components, and then test the CubeSat and launch in operational environments, and to create a website for funding and design for future missions. This is our team breakdown. We have project lead and project manager, and then we are 5 sub-teams: the communications team, systems team, thermal management team, solar power, and the business team. And then we have 12 members total. So this is our timeline for the next 2 quarters. We have it broken down by different milestones at the top, and then our objectives and the tasks according to those objectives. Some important dates for the next 2 quarters. In the last 10th week of spring quarter, we hope to perform a day in the life test, which is basically just a 24-hour operation cycle of the CubeSat. And then in fall quarter of 2019, we hope to begin doing our vibrations test, thermal vacuum test, shock testing, and acoustic testing. And then finally, we hope to launch at the first quarter of 2020. So now I'm going to hand it off to Elena to talk about the budget.
Thank you, Roland. So on the first figure, you can see how our spending this quarter was distributed. The most money was spent by solar panel team, mostly because they needed new equipment in order to manufacture solar panels. In the second picture, you can see the estimates of our future spendings. And 3 most important stuff we need also happen to be the most expensive ones. One of them is transceiver board. There. The second one is testing, but this number is not final yet because it accounts only for thermal and shock testing, and we're still waiting for quotes for acoustic and vibration testing. And the last one is launch, which is, luckily for us, the most expensive, and it's already covered by NASA. On the next slide, you can see the comparison between our current budget, which is in green, and the funds we needed in order to finish the project. Comparison is not in our favor. So we decided to raise some funds through the website. Right now, the website is still under development, but we're aiming to create an affordable, informative, and professional website which will attract the attention of the possible investors to our project. We're also working on a CDP fund proposal right now, so we're hoping to get some funds from them as well. And now Walden will talk about communications team.
So the communications team is responsible for designing the transceiver to transmit the payload experiment, position, and thermal data to the ground station. We are also designing the ground station, which will transmit controls to the transceiver as well as receive signals from the transceiver. The requirements for the transceiver is to successfully downlink the data in 90-minute orbit in 3 or 4-minute windows. For the ground station, the requirements is to transmit the signal with power of 1 watt or less. This is due to FCC regulations. So far this quarter, we've completed an ANSYS simulation of gain and of our ground station antenna, which you can see in the chart over there. We've also picked the transceiver design from UCICubeSat, which is the one we'll be using. in progress for this quarter, we're going to be finalizing the link budget, which includes all the gains and losses of the antennas and the transceivers to finalize our antenna design. We are also finalizing our downlink data rate and bit error rate to determine our modulation scheme. Our next goals are to coordinate frequencies with the International Amateur Radio Union and to test the ground station of orbiting satellites. So next is solar team.
So for part of solar team, our task is to provide the CubeSat with the maximum power possible. And we've been testing various fabrication methods, one of which involves a oven soldering process, which works relatively well for these solar cells. The other includes hot air solder to be able to connect these two terminals here in order so that we don't short circuit the PCB board. So in progress still is fabrication of the other solar arrays, and so our next steps are to test under vacuum, vibrational tests, and shock tests. We are also planning on designing a power output circuit, or power control circuit. So then, thermal management.
So what is thermal management in the case for our satellite? So STK simulations in the past have told us that our battery is going to be cold on the dark side of the Earth during orbit. So we need a heating element to regulate the battery temperature. This STK simulation outlined a few requirements that are going to be driving this design. First is a minimum of 13.15 watt power dissipation to keep the battery at temp. And so we want a safety factor of at least 3, so multiply that power by 3, and that is our maximum power output of our heating element. And second, it comes from the batteries. The batteries can output 6.5 amp current at a maximum. That's the main number we need to consider for our design. So we've completed our design of the heating element. We used nichrome wire, and the length was calculated based on the requirements. On the first picture there, you can see our first completed heating element covering our batteries. It has tape on both sides that is thermally conductive but electrically insulating. The next picture, you can see a render of our heating element guide. This is 3D printed and glued together. That guide traces the heating element so we can actually build it. These are wraps. It's hard to do by hand. So from now on, we're going to be creating a nicer version of the heating element. It's a little bit messy. It's our first one, so we want to make a nicer one that we can present and it be functional. So because we are almost done with heating element, we need to start our systems control because we need to control this heating element from an input temperature from the batteries. It's a little bit hard to see on this projector, but this is a temperature as a function of time of the heating element. As you can see, it's an exponential decay. So we need to run a test in a vacuum chamber to determine how long it takes for the heating element to reach 95–98% of its final value. That value is really important when you're designing your control system. And from that, we're going to integrate it with the rest of the system on the CubeSat. So next, TQ is going to talk about systems.
So the purpose of systems is to ensure that our CubeSat meets the requirements of NASA and any other requirements that may be required for us to launch into space. To ensure that we will be conducting 3 tests, which are the shock test and the thermal vacuum test, both of which will simulate the harsh condition that the CubeSat undergoes while launching into space in the rocket. And the third is, as Erling mentioned before, the day-in-the-life testing sequence. This is essentially to make sure that our CubeSat can maintain functionality throughout a 24-hour period and that it will keep operating as so while it is in space. To accomplish that goal, so far, as you can see on the slide, we've created a SolidWorks sketch to model everything, how everything fits together. And also we've created a list of requirements, snapshot of which are shown here, and other paperwork that are required before we can actually file for launch. And in progress, as Elena mentioned before, budgeting relies heavily on our testing, which because it varies so much on what we're testing and where we're testing it. So we're currently looking at national technical systems to test upwards towards LA, but we're also looking for more quotes to ensure that we don't have to spend, we have to spend as little as possible. And for our next steps, we will be looking for ways to successfully deorbit our satellite after our 6-month mission to ensure that we can minimize space junk. And also, we'll be beginning to follow paperwork with the NOAA, the FCC, and the ITU to ensure that we have the radio frequencies required to communicate back and forth to our CubeSat through our ground station.
Okay. Thanks, everyone. Is there any questions?